In this video, I'd like to discuss the basics of crosstalk as it applies to PCB and hardware design, go through some real-world measurements of crosstalk, and then also discuss how you can reduce and hopefully mitigate crosstalk to a certain extent in your own PCB and hardware designs. This will go through some practical tips, looking at actual implementations in terms of your stack-up, geometries, trace spacing, feature spacing, rise times, and much, much more. The PCBs we'll be looking at for demonstration and measurements, some of we've seen a couple times on this channel. So on the left-hand side, we have this Queen Bee radio control PCB, where I'll be doing some rather simplified crosstalk measurements of aggressor and victim traces and see how even with pretty well-spaced traces, by changing their output, rise and fall times, we can get pretty aggressive crosstalk despite good spacing and despite close reference planes. Also, for more simplified test, we will be looking at two microstrip traces, one aggressor and one victim line, to measure crosstalk using a real-world system, seeing what near-end crosstalk is, far-end crosstalk, and how that influences our design choices as PCB designers and what we need to pay attention to. Keep in mind, this is only an introductory video, and I'll be leaving a lot of information and other resources and references in the links in the description box below. A huge thank you to JLCPCB for sponsoring this video. I had these Queen Bee radio control PCBs manufactured and assembled by JLCPCB, and they did an absolutely fantastic job. JLCPCB provides easy, affordable, and reliable PCB and PCBA solutions, which really empowers electronics engineers to develop projects efficiently and quickly. JLC is super easy to use. We simply have to click on Instant Quote, add our Gerber files if we just want PCBs, or if you want assembly, you can very easily add your PCB bill of materials and component placement files, and that's pretty much all you need. Their pricing is truly incredible. For instance, for 6 and 8 layer PCBs at 50 by 50 millimeters, we only paid $2 for a set of 5, which I think is pretty incredible. They can achieve this pricing due to large scale production, which reduces their and our costs. I've had a super good experience with JLCPCB, and I'm very grateful that they sponsor this channel. I can get my PCBs fully assembled back in about a week's time, which is amazing. Not only is their lead time super fast, but their quality is top notch as well. So I'd highly suggest you check them out. Links will be in the description box below as usual. Another huge thank you also to Altium for sponsoring this video. If you'd like to give the powerful Altium 365 platform a try, make sure to follow the link in the description box below, or go to altium365.com/YT/Phil's Lab, and you can get yourself an Altium 365 free trial. Altium 365 brings many impressive features to Altium Designer, such as collaborative design, design reviews, mechanical co-design with SolidWorks, Fusion and more, manufacturing collaboration, easy bill of material management, and much, much more. If you'd like to check out in part some of the cool Altium 365 features, make sure to go to my GitHub profile or go to pms67.github.io and check out some example hardware designs that were shown on the YouTube channel and also for this particular video. You can check out a couple of the boards, for instance, the Queen Bee controller for the micro quadcopter using the Altium 365 viewer. You can check out the schematic, PCB, look into all the routing and all of the layers in real time, and also of course check out the 3D view, which I think is super useful, especially when you're sharing designs with people maybe even outside of your organization. I'll leave links in the description box below, and thanks for checking them out. Let's start off with the crosstalk basics. Effectively, crosstalk, when it comes to PCB design, is the unwanted transfer of energy from one element. So this could be a trace, this could be an IC, a component such as an induct and so on, and we typically call this the aggressor. This aggressor transfers unwanted energy to another element, which we'll be calling the victim. Again, the victim could be a trace, it could be a component, a plane, any element that we can couple to. Of course, there can be multiple aggressors and multiple victims, but we typically boil down the problem to a single aggressor, which is our active driven line, for example, and a victim, which is passive and is effectively just a receiver. The way this unwanted transfer of energy occurs is by capacitive and inductive means. Capacitive means through E fields, so electric fields, and inductive means through H fields or magnetic fields. A very simple illustration of this we can see on the top right-hand side, where we have an aggressor trace on the left-hand side, a victim trace on the right-hand side. These are run above a solid ground plane below, separated by a dielectric of a certain material and thickness. This capacitive and inductive coupling happens through parasitic elements such as parasitic capacitance, as well as parasitic inductance, which then forms the mutual inductance between aggressor and victim lines. Crosstalk then occurs when we drive, for example, the aggressor line with changing signals, so changing voltages and changing currents. So we have these dV by dt, so changing voltage with respect to time, and di by dt, so changing currents with respect to time. These changing signals, and it's important that these are changing, trigger these crosstalk events very simply speaking. Again, due to these stray and parasitic capacitances and inductances. Although this happens, of course, in the analog domain as well, such as RF, audio, and so on, in this video we'll be looking predominantly at digital signals. For digital signals, we typically have square waves, or in the real world, trapezoidal signals, for example, shown in the middle here, where we have two states typically for binary system, logic low and logic high, and they transition in a finite time from one to the other. So starting from a logic low to logic high, and maybe back down again. During this transition, we have these rising and falling edges. Now, for modern logic, these can be very fast in the nanosecond or sub-nanosecond range, and depending on the ICs we use and how we lay out these ICs and traces, we'll get differing edge rates, so both rising and falling. When it comes to crosstalk, the crosstalk or the amount of coupling is worse, so to speak, at faster edge rates. So for the same physical parameters, if we have faster edge rates, so shorter times for these transitions, we'll get more crosstalk for the same scenario. And we'll see more of this later on. Some examples of where crosstalk is important and can be very detrimental. For example, if we run a digital clock signal close or next to an analog ADC input trace. If there's too much crosstalk, too much coupling, we might get wrong ADC readings, especially if you have a very high bit depth or high resolution ADC, maybe a 16-bit, 24-bit ADC in audio. Additionally, we can get crosstalk problems in memory buses, for example, DDR memory buses, where we usually have many parallel, tightly packed high-speed traces. Coupling could lead to data errors if we get voltages induced on victim lines, we get timing errors, which may in turn lead us to use lower bit rates or data rates. An example of a high-speed DDR3 memory interface we can see on this set bread that I designed, where we have a system on chip as a main processor, as well as 1 GB of DDR3 memory. Across several layers, we have this wide parallel bus which belongs to DDR memory. Due to space constraints and feature sizes, we have to pack quite a lot of high-speed traces rather close together. As these are all high-speed digital traces with fast edge rates, we can have quite considerable crosstalk amongst these traces. We might also have, as an example, a fast digital communication line close to a processor reset trace. With a high enough voltage, fast enough edge rate, and enough coupling due to our crosstalk, we could even trigger spurious resets from this fast digital communication line, which couple over to our processor reset line. And these are just a few examples. Of course, there are many, many more, but I'd like to use that to illustrate that crosstalk is and can be a very severe problem in PCB designs. Lastly, on the right-hand side, I've taken this from a Rick Hartley seminar. We can see a microstrip at the top, which is an external layer trace, and a strip line trace on the bottom, which is an internal layer trace. We can see the electric and magnetic fields do spread out quite considerably around this trace. So if we're assuming this is an aggressor trace and we bring a victim trace in close, you can see that these fields will also interfere with the fields of another trace, very simply speaking. Let's briefly go over forward and backward crosstalk, but keep in mind this is a terribly involved subject, and after this slide I will be showing you some recommended videos to watch, which goes in far more depth on forward and backward or far end and near end crosstalk, videos by Zach Peterson of Altium Academy, as well as Eric Bogerton and Robert Ferenek, and these are several hour-long videos in total, which we can't unfortunately fit into this video. It's important to know that when discussing forward and backward or generally crosstalk, that there are differences between the geometries that we use. So if we use a microstrip, that is an external layer trace, or if we use a strip line, so an internal layer trace on our PCBs, the crosstalk behavior actually does change, and you will see that in the suggested videos in just a minute. Our typical setup is shown below, very simplified. Again, we have an aggressor system, which is fed by, let's say, some sort of trapezoidal or square wave digital source through an output buffer along a transmission line or trace into a receiving buffer or receiving end. Similarly, we have exactly the same setup on the victim side, except that the victim buffer is only driven by a logic low, so it's a quiet low signal. There's no intrinsic activity other than the victim buffer's noise, plus any crosstalk that happens on this victim trace. When we then come to crosstalk, we have forward and backward crosstalk. Forward also being referred to as far end or FEXT, backward also being referred to as near end or NEXT. Forward crosstalk is measured at the receiving end of the victim line. So this this would be at the receiving end, the receiving buffer of the victim line. That is forward or far end crosstalk typically. Very generally speaking, this typically requires fairly long parallel runs to cause significant problems. The forward crosstalk that appears on the victim line travels in the same direction as the signal on the aggressor trace. So in this particular image, this would go from left to right. On the contrary, looking at backward or near-end crosstalk, this is then measured at the transmitting end of the victim line. Again, generally speaking, this is typically greater per unit coupled length than forward crosstalk, and problems may arise sooner. Contrary to the forward crosstalk, backward crosstalk, as the name implies, travels in the opposite direction to the signal on the aggressor trace. So if the aggressor trace signal goes from left to right, the backward crosstalk signal would go from right to left. Do note, however, that the naming of backward, far end, near end can change depending on switching directions, relative orientations of aggressor and victim interconnects, and more. I won't be going into terribly much detail on far end and near end crosstalk, so for the measurements later in this video, I'd strongly suggest checking out a few videos and books if you are interested, as that will definitely help you understand crosstalk more and in which situations it applies. Also, the difference between microstrip and stripline crosstalk. First of all, we have a video by Zach Peterson on Altium Academy titled "What are the types of crosstalk in PCB design?" Links will be in the description box below. And then there are 2 videos on Robert Feranik's channel which feature Eric Bogatin, which are great videos to visualize near-end and far-end crosstalk for microstrip and stripline configurations. Again, links will be in the description box below, and I would strongly suggest you pause this current video right now, watch these, of course, if you have the time, and then continue back with this video when we look at some measurements and look how to reduce crosstalk in our designs. I'd highly recommend checking out a crosstalk calculator, and these are freely available on the internet, and I'll leave a link to this one in the description box below. This will depend if you're routing as a microstrip or stripline, but this one we're looking at microstrip, so an external layer trace. Here we can see we have, for example, an aggressor trace and a victim trace side by side, separated by a spacing S, and they are a distance h above, for example, a reference plane, a ground plane, for example. Crosstalk depends on various factors. For example, the aggressor or the source rise time, the aggressor or source voltage, how long we route these parallel lengths together, so for what distance are these traces spaced by this separation S. The crosstalk depends on the substrate height, so how far away we are from the ground plane, as well as the trace spacing, of course, and the substrate dielectric. Let's go with a substrate dielectric, maybe 4, a substrate height, let's say for a 4-layer board, that might be 0.1 or 0.2 millimeters, and we have a typical source voltage, let's say of 3.3 volts. Of course, this is fairly arbitrary. I'd suggest you play around with these. These are fairly typical numbers. A source rise time for a microcontroller might be in the order of nanoseconds, and a particularly fast microcontroller might even go down to 1 nanosecond rise time. Then we can play around with the length of parallel routes and the trace spacing and see what the coupled voltage is from the aggressor to the victim line. If we have a 1 centimeter parallel route and a trace spacing of 0.1 millimeters, we can see we have quite a lot of coupled voltage only for 10 millimeters, so 1 centimeter, of about 2.64 volts. If we increase the length of parallel routes to 10 centimeters, you can see the coupled voltage actually doesn't change. This is because, remembering back to this graph on the bottom right, that we've already exceeded the critical length. Because backward crosstalk is typically dominant, we have to stay under the coupled length for the length to have any effect. And that's what we see here. So if I reduce it back to 1 centimeter, it doesn't change, but if I change it to 0.8, 0.5, 0.4, we can see the length of parallel routes has an impact. But we can see that 0.8 centimeters or 8 millimeters is pretty much our critical length in this particular scenario. And this is already very, very short. We'll see the implications of this later on as well. What we can also change, of course, is maybe the substrate height. So increasing the substrate height means we have a greater coupled voltage. And this is because we typically get a greater field spread, as we can see in the image on the bottom right-hand side. If we increase the trace spacing, we would expect the crosstalk to drop. So if I triple the trace spacing, you can see the crosstalk has dropped quite considerably. If I increase the voltage, of course, we get more coupled as well. If I increase the rise time, I get less coupled voltage. So I'd strongly suggest playing around and getting a feel for what parameters influence this crosstalk and the coupled voltage magnitude. What we also have to be concerned with is, of course, how much crosstalk can we actually tolerate. These numbers, just as they are, 1 volt, 0.5 volts, they don't really make any sense as such. It's always dependent on the application and dependent on the situation. So we can either use a crosstalk calculator, as we just saw, or a simulation tool, which I'll show you in just a second. Some very, very simplified examples might be if we have a digital line running close to an ADC input line or trace, how much crosstalk corresponds to 1 bit of error in this particular ADC. That ADC of a simple microcontroller might have only 10 bits, which means we get 2 to the 10, so 1024 discrete levels. Let's say the ADC voltage range is the same as that of the microcontroller, which is powered off 3.3 volts, which means a least significant 1 bit, we have a resolution of about 3.2 millivolts. Then we have to ask the question, what is our PCB routing like? Are we routing as a microstrip, so an external layer trace or internal layer trace? What's the dielectric thickness, the material? What is the edge rate and the voltage of the aggressor, so maybe of our digital line that runs close to this ADC trace? And what's the length of a parallel run? And from this information, we can then get a minimum spacing to that ADC trace. I've just taken some fairly random values, so dielectric thickness of 0.1 millimeters, a microstrip trace, dielectric constant of 4, a rise time of 10 nanoseconds of the aggressor running at 3.3 volts, and I'm letting them run for 50 millimeters coupled length, so this parallel run. That gives me, plugging this into a calculator, that I need to have a spacing of at least 2.6 millimeters between my aggressor and my victim trace, so that I just get below 1 bit of error. And of course, you'd like to keep them wider than that spacing as well. But this might be a good starting point. Similarly, we could look at a different example, looking at how much crosstalk would trigger a microcontroller reset. In this case, our MCU might be running at 1.8 volts. If it's a CMOS reset, then that high-level reset might be at 1.17 volts. And then again, we can ask various questions. What are the PCB materials, the thicknesses, the edge rates of the aggressors, and so on? And in this case, we might want to ask, for a given trace spacing, what is the parallel run length maximum allowed to not trigger a reset? So for a 5 volt, 1 nanosecond rise time signal, which could be a bit hard to achieve, a spacing of 0.18 millimeters between aggressor and victim, we might get a parallel run length of maximum of 7.8 millimeters before we get too much crosstalk. Again, these are very, very simplified examples, but just to show that it depends on the application of how much crosstalk we can tolerate, and you have quite a number of parameters to play with. Let's briefly measure far-end and near-end crosstalk using a very simple measurement setup. This is a demo PCB I made with just 3 microstrip traces on a 2-layer PCB, and the width is wide because this is a rather thick PCB at 1.6 millimeters, and therefore to get a 50 ohms trace I had to make fairly wide traces. I need this using an impedance calculator. On either end of each trace we have a UFL connection which I can hook up to a signal generator, oscilloscope, or whatever else I need. In this particular case we are only concerned with the lower 2 traces. The middle trace will be our aggressor trace, where I'm feeding in from a signal generator source, which is controlled by my oscilloscope, fed via 50 ohm input through this 50 ohm controlled impedance microstrip trace, and I've soldered on a 50 ohm termination resistor, and I'm just monitoring that with a high impedance probe connected to channel 1 of my oscilloscope just as the trigger input. And so we can see the rising and falling edges and also just the general waveform of our signal generator source. This aggressor trace will then capacitively and inductively couple over to the victim trace, which is the lowest microstrip trace. Here I also have 2 UFL connections, one which is close to the signal generator source input. This is where we'll be measuring the near-end crosstalk. This goes to a channel on my oscilloscope which is set to 50 ohms input. On the left-hand side we also have a UFL connection which goes to an additional channel on my oscilloscope where we can see and observe the far-end crosstalk. And the scope setting for that is also on 50 ohms input. So a very, very simple setup. The traces are quite far apart and therefore we won't see terribly much crosstalk, but we'll be able to examine the effects of frequency, rise time, and look at near-end and far-end crosstalk and their differences and similarities. For the signal generator, I'm just using a Siglent standard wave generator which can be controlled by my oscilloscope, which is this Siglent SDS6204A, where I have 3 channels set up as we just previously talked about. I have my channels set up as follows. The yellow channel right at the top, I've offset all these channels so they don't overlap. The yellow channel at the top is my source. This is coming from the WaveGen. I can control via the oscilloscope. If I go to Utility and WaveGen, we can see it's currently set to a square wave with a 1 MHz fundamental frequency and an amplitude of 3 volts peak to peak. Duty cycle 50% and no DC offset. What I've added also at the bottom of the screen, you can see various measurements, that is the rise and fall times, and this is unfortunately not adjustable for this particular WaveGen, and this is at 25 nanoseconds, so fairly slow. Typical microcontrollers these days might go from anywhere from 1 to 10 nanoseconds, depending on the output drive strength, so this might not be entirely representative of a GPIO output, for instance. I've also added peak-to-peak measurements, so channel 1, channel 2, and channel 3, where channel 2, the trace in the middle, which is centered, is the near-end crosstalk crosstalk measurement, and channel 3 is the far end crosstalk measurement. We can see the scale divisions at the bottom. For the yellow trace, this is 2 volts per division. For channel 2 and channel 3, this is only 1 millivolt per division. Also looking at the measurements currently, peak-to-peak measurements, we are getting very, very small values because these traces are so far apart, because our rise times are small and our frequency content is small in the aggressor trace. We will be playing around with this in just a second. For now, let's initially just zoom in on one of these rising edges of our trigger waveform. So I'm going to change my time base down to 20 nanoseconds per division, and we can see what's going on a bit clearer. On the rising edge of my input aggressor waveform, we can see on the near end crosstalk, we are getting a positive going pulse, which has a similar time width as our rising edge. On the contrary, although the pulse does look similar, for the far end crosstalk, the third trace right at the bottom, this is now inverted. So this is a negative going waveform. Looking at our measurements, we can see the peak to peak of our near end crosstalk, our middle trace, is only about 1.6 millivolts on average, and our far end crosstalk is only about 1 millivolt, so less than our near end crosstalk. Now, given that we have a pretty large amplitude aggressor signal, we are not getting very much crosstalk at all, both for near end and far end. Again, this is because our rise time is pretty slow and our frequency content of the aggressor signal is pretty slow. We have pretty far away spaced traces. So this is a pretty good situation, but we do see that we can measure this. And imagine bringing the traces closer, increasing the rise and fall times, you would get far more crosstalk. Here, again, refer to the calculator. We can also look at the falling edge if I change my trigger to falling, and we can see now the near end and far end crosstalk are flipped in accordance now with the falling edge of our aggressor signal. And keep in mind, this is for microstrip trace. Things would be slightly different if we're using a strip line trace, but this is just for the sake of demonstration. What we can now do is play around with the wavegen signal. So if I go to utility wavegen, I can of course adjust my amplitude. So as I start reducing my amplitude, let's say down to 2 volts, peak to peak, we can also see the crosstalk reduces further as well. So it's proportional in some way to the amplitude of the aggressor, which makes sense. I would like to, of course, be able to change the rise time. Again, I'm not able to do this for this particular wavegen, but I can change my square wave to a sine wave. So adjusting the wave type to a sine wave, I'm going to increase my amplitude to something larger, and then you can immediately see the effect on the near end crosstalk, the middle trace, and the bottom trace, the far end crosstalk. The near end crosstalk is following the rising and falling slopes of the sine wave, whereas the far end is as well, but it is inverted. So on a rising slope, we are getting a negative going or trough on the far end crosstalk. Now, if I go to the wavegen and increase my frequency, we can see what happens to the crosstalk. So if I go from 1 to 5 megahertz, we can see the crosstalk increases as well. We're getting a higher amplitude crosstalk for both the near end and far end crosstalk, which is indicative that the higher frequency content we have, if that's an analog sine wave or if it's a digital square wave with faster, that is shorter rise and fall times, we know that we will get a higher magnitude of crosstalk given the same geometry and voltages as well. I can increase this even further, for instance to 25 megahertz, and now I also have to change my scale divisions on the far end and near end crosstalk to make it fit. So changing to 5 millivolts per division, we can see now for 25 megahertz sine wave, we're getting about 6.5 millivolts peak to peak on the near end crosstalk and about just over 4 millivolts far end crosstalk for this 25 megahertz sine wave. So just to show that the frequency content and voltages of course make a difference given the aggressor and will influence and really increase your crosstalk on the victim trace. Just to show you a more real-world practical demonstration, I'd also like to show you a quick measurement or two on the Queen Bee radio control PCB that's featured a couple times on this channel. And for this experiment, I'm simply setting up the STM32H7 microcontroller, one aggressor output, which will just be a 100 kilohertz timer square wave where I can control the output drive strength, which gives me rise and fall times adjustable from about 1 nanosecond to about 6, 7, 8 nanoseconds. So we can see the impact on increasing and decreasing the rise and fall times on the crosstalk. And another output channel I'm just going to be driving as GPIO low, which will be then our victim trace. The two traces you are seeing here are the aggressor and victim, which are routed for a fairly long parallel length, still spaced quite a good amount apart, but we can see even with this spacing that we do see quite a considerable amount of crosstalk, which is dependent on the rise and fall times. So having uploaded the code to the board, I'm currently just measuring crosstalk right at the trace end. This is unterminated as well, so I just have high impedance inputs to my scope. The yellow trace is my clock signal, and currently we're just zoomed in on the rising edge. This is with a low GPIO output drive strength. So on the bottom left, you can see the rise time measurement is just about 8 nanoseconds. So faster than the SIGGEN we just saw, but it's still comparatively slow at 8 nanoseconds. The second trace is the crosstalk measurement on the quite low output of the STM32, so this is just set to a GPIO low, but we do see quite a bit of crosstalk already. The smaller periodic bumps you are seeing is actually clock feed through from my 25 megahertz high-speed external crystal oscillator, so ignore those. What we're interested in is what happens shortly after the rising or falling edges. So shortly after the rising and falling edges, for these two particular traces, the victim trace is showing about 40 millivolts of peak-to-peak crosstalk for an 8 nanosecond rise time after a rising edge. And similarly, looking at a falling edge, the fall time is a bit slower, so at about 8.4 nanoseconds, but still quite similar. On the falling edge, we are seeing about 31 millivolts of peak-to-peak crosstalk. Given this system is 3 volts logic, that is still pretty good at about 1% crosstalk. Now, let's see what happens if we increase the output drive strength of our aggressor and bring down our rise and fall times. Here I've now adjusted the GPIO output drive strength of the aggressor signal, and what we can already see on the yellow trace is that we do get ringing because this is an unterminated, fairly long line, which means we get reflections. Again, this causes ringing and overshoot and undershoot, so it's not entirely a fair comparison because this ringing will also be apparent in the crosstalk we are seeing. However, looking at the rise time, this is down to about 1 nanosecond, so we have much faster rising edges, which also leads to considerably more crosstalk, other than the fact that we are also getting reflections and ringing in the crosstalk waveform itself, which you can see on the second trace, which is this pink purplish trace. Looking at the peak-to-peak measurement, we're getting 10 to 15 times more crosstalk just because we've shortened the rise time quite considerably. So be aware of that when you're adjusting your rise and fall times, and you might want to slow down your rise and fall times to reduce crosstalk if possible. Of course, we see something similar on the falling edge. Again, we get undershoot and ringing due to the reflections of this unterminated line. Just for very simple demonstration purposes, we get something very similar on the falling edge. Pretty considerable crosstalk, also due to reflections and ringing, and that's almost at half a volt, which is considerably higher than just going with the slow and more adequate rise and fall times set previously. After having examined the very basics of crosstalk, this then brings us to the topic of how do we even reduce crosstalk and what are some options we have to influence the crosstalk behavior. And we have already seen quite a few by looking at the calculators and also the signal integrity simulation tools. The main way of reducing crosstalk, as you've probably seen and noticed, is to increase space between elements. Now this is trace to trace, it could be trace to aggressor planes or to aggressor components, and this is both in the XY, so in the planar space, but also in the Z direction. So maybe putting one trace on one layer and a trace on a different layer separated by a ground plane will aid with your crosstalk. IPC recommends for microstrips to have a 2H spacing, so H being the dielectric thickness from the signal layer to a reference layer, and for strip lines 1H. However, this is of course entirely situation dependent. If you really have to have a lot of isolation, so reduce the amount of crosstalk you have between traces, you'll have to probably space them much further apart. For example, in this PCB, these traces are part of a gigabit Ethernet interface between a MAC and a PHY, and you can see any place I can, I'll try and space out my traces. And this is not just the traces themselves, so I could have them of course close as this, but this would increase the crosstalk, so I space them out as much as I can. But also these delay matching meanders, I want to space them out as well, because of course we can have intertrace crosstalk, for example. In some cases, for example, this DDR memory bus or this part of this DDR memory bus, we have a lot of parallel traces that are forced to run very close together, but we still want to do as much as we can so we don't squeeze them together like so, but we maximize our space between them, again, for crosstalk reasons. What we can also do to reduce the amount of crosstalk is to decrease the distance from, for example, signal power layers to reference layers. So moving our signal layer closer to a ground reference. As we saw in the simulation tool, for that particular example, when we doubled the dielectric thickness, we actually doubled the crosstalk. Of course, again, situation dependent. Typically for thinner dielectrics, we get less field spread and in turn, less crosstalk. We also want to maintain solid return paths, so avoid splits, which lead to field spread and which increases crosstalk as well. If you can, and if your cost allows it, I would strongly suggest to avoid signal layers adjacent to other signal layers. So for example, the stack up you see on the bottom right-hand side, we have signal, ground, ground, signal. So at least one reference plane between each signal layer. If this is unavoidable, what you can of course do is route one of those signal layers adjacent to the one horizontally and the other vertically. And this reduces the crosstalk significantly. Here are some additional ideas, and a lot of these can be much harder to implement. The main takeaway should be that spacing is what's important to minimize crosstalk and bringing reference planes closer. In certain cases, what we see on this slide can aid to reduce crosstalk, and sometimes they can't. For example, reducing parallel lengths and runs. As we saw before, on the right-hand side, we have this magnitude versus coupled length. We see that backward crosstalk dominates and dominates very quickly. So we don't have very much length before we've hit the maximum backward crosstalk anyway. So many times it's not feasible to minimize your maximum length because you've exceeded that anyway, that critical length. Oftentimes have to route traces parallel to each other. Again, referring to this address command and control signal part of the DDR3 memory bus, there isn't much other way of doing this, and we do have these rather long parallel runs. What we can also try to do, if we don't specifically need them, is to increase the rise and fall times. So longer rise and fall times typically means less coupling. So that could mean choosing slower ICs, so to speak. So maybe finding a microcontroller that will do the job but has slower rise and fall times. You might have programmable drive strengths or programmable rise and fall times in many microcontrollers and FPGAs, and maybe even a small series output resistor to adjust the slew rate of that driver, which leads on to termination. But keep in mind, increasing rise and fall times, oftentimes we don't have control over. So it's kind of a secondary thought to reducing crosstalk. Termination can help, as we saw in the simulation, but of course that's very situation dependent. It depends on the whole architecture of the rest of the system anyway. We shouldn't just add in termination for the sake of adding termination. It needs to be carefully planned depending on the situation, and again, this will be covered in a future video. Shielding, of course, is also possible, and that also interplays with routing a strip line versus microstrip. Microstrip, we have a trace above a plane, and that trace is exposed effectively to the surrounding environment. Whereas a strip line, we have a plane above and below, so we might get a better shielding benefit and thus reduce field spread and thus crosstalk. Shielding could also happen in the form of shielding cans, which you'll often see in RF and microwave designs. Lastly, a very interesting point is if you should place ground fills between traces. Oftentimes it might seem like a good idea, as that naively thinking could be seen as a shield. For example, very crudely drawn here, you would maybe do this with a copper film. We have the aggressor trace, the victim trace, separated by distance, but additionally, we've added in this strip of grounded trace attached to ground at both ends. And this is typically a very, very bad idea. This might act as an antenna or even as a bandpass filter between the aggressor and the victim line, and maybe even increase crosstalk. If you really want to do this or must do this, this needs to be carefully planned. You need to place many or enough stitching vias on this grounded trace in the center to make sure it doesn't resonate and doesn't act as a bandpass filter. The spacing of these vias depends on the maximum frequency in the system, in turn which depends on the edge rates in the system. In general, it's probably better if you don't want to calculate and don't want to worry about it, just to get rid of that. There isn't much to be gained anyway, even if you get it to work right. The main takeaway should be maximize your spacing between aggressors and victims. Thank you very much for watching this video. I hope it was useful, and I hope it showed you the basics of crosstalk, how it appears in victim waveforms depending on if it's microstrip, strip line, near end or far end, and what you can do on a PCB and hardware level to reduce levels of crosstalk in your design, and also of course why you would want to reduce crosstalk in your design. If you liked the video, please leave a like, a comment if you have any questions, and don't forget to subscribe to stay up to date with any latest PCB, hardware design, and embedded systems videos. Thanks a lot for watching, and I hope to see you in the next one. Bye bye.